I'm excited that we convinced Mike Luby to give us a talk. Mike, of course, is famous for a great deal of research on air encrypting codes. Before he went into implementation and started Digital Fountain, which they sold to Qualcomm. I guess he did his time there. And now he's with BitRipple. So I'm excited to hear what he's going to tell us about erasure codes and interactions over networks.
Okay. Thank you. So this was a long trip for me. I live right up the hill. Oh, I'm supposed to use this. Okay, good. Then I can walk around. That's always good. So yeah, I'm going to be talking about applications of erasure codes for enabling interaction over networks. This is BitRipple's founding team. It's myself, and you probably recognize, some of you recognize Lawrence. He was a PhD student with Amin Chakravarti over at EPFL, and then he came and did a postdoc here at Berkeley, and after that I nabbed him, and we worked together at Qualcomm for many years. And then Pooja was someone who was also working within Qualcomm for several years on really interesting projects, MediaFlow, ATG, and computer team before we met each other, and she ended up working together, the three of us as a team, for many years at Qualcomm. And then when we left Qualcomm, we went off and started BitRipple. So that's kind of where the genesis of the technology comes from. And in many ways, it's very similar to what Digital Fountain was all about. Only Digital Fountain was probably 20 years too early, I hope. Which means that it's about the right time for this technology to be. And the applications have changed. Back in the days of Digital Fountain, we had things like, we were supporting the Harry Potter films, like when they were doing the digital daily shoots over in New Zealand. We were the ones moving the data over to Burbank every day so they could see what the film was, so they could tell them what to do and then shoot the next day. And also for things like the Harry Potter was in England, but the Lord of the Rings was in New Zealand. And so those are the kind of things that we're involved in there. And we had a bunch of IPTV things and so on. But the world has changed. The world has changed. And the way it's changed is that interaction and latency are much, much, much more important than they were back then. Barely back then could you get data across networks. Now you can get it across. But now the new paradigm is to get it across quickly. So in terms of the company, I like this term. I just kind of made it up a few days ago, virtual interactive network. It's kind of like a VPN. Only it's a VIN. So to enable these flawless interactive experiences. And it has a bunch of applications. So these are things where interaction really matters. Cloud gaming, AR, VR, telematics, remote collaboration, things like that, right? Competitive advantages. So we can, as I'll show you in a couple of slides, get a much more responsive user experience, predictable low latency data delivery mostly over wireless networks. Those are the challenging ones. And something that is very crucial is a strategy where it's scalable and flexible to integrate into existing solutions. And I'll show you that as well. So that's really an important aspect of the overall solution. So some of the problems solved, it eliminates stalls, jags, jitter, pixelation. I'll show you some real examples of that a little bit later, some real operating things, and see the difference. You'll see it. Predictable experience over wireless and increases data delivery robustness. So these are some of the market trends that are driving this initiative that we have. So things are tending to be driving towards the lower and lower latency regime. So when you're watching, for example, online video over Netflix or Hulu or YouTube, if you look at the stats, which you can click on the button and see what the stats are, they're buffering 20, 30 seconds of video all the time. And because of that, they can afford to have a lot of back and forth in terms of how they deliver that data. And they're really not that worried about latency at all. When you get to video conferencing, video chat, quality tends to be a little bit lower, but the latencies are much tighter. There may be 100, 200 milliseconds, something like that. And then as you drive forward to these cloud gaming AR, VR, it's like every millisecond counts. that they're really in that regime at some point. So that's what we're driving. And also the content quality is also important. By the way, if anybody has any questions or comments or whatever, I don't think I'm going to go the full 40 minutes, and I think that's still true, but I'm sure I'll find a way to go. So this is kind of a slide of, opportunities, as I mentioned, cloud gaming, AR, VR, telematics, remote collaboration. As I mentioned before, stalls, lags, jitter, pixelation are an issue. So here's an example of Xbox cloud gaming. This is the Microsoft cloud gaming platform that's out there. And this is a screenshot of when the experience was not particularly good, as an example. So that's the kind of thing that we're kind of trying to clean up. So let me just talk, and this is really conceptually at a very high level how the solution works. So other solutions, pretty much everything out there, WebEx, Quick, RTP, every other delivery solution out there is based on retransmission when you lose packets. So you send the data across the network, and then there's feedback that comes the other way that tells you what you lost. And then you send those lost portions, and you get feedback whether they got there or not, and then you send them again, and that keeps going back and forth. And so if your network is clean, you can get your data across in one shot, and that's great. You get it across in the first pass. If the network is a little bit dirty, it doesn't have to be that dirty to get it to have to go back and forth multiple times, then you get, if you want to really get the data there reliably, it takes a lot longer. In this example, 5 times across the network instead of just once, right? And that amount is variable depending on your network conditions. So your quality of experience really varies as your network quality varies. So you have 2 options with those solutions. Either you have variable delivery time, which means you have jags and stalls and jitter and all that other bad stuff. Or you decide, I'm going to have a fixed latency budget, and I'm going to cut it off here, right? In which case, you're gonna see pixelation. You're gonna see all this other stuff, bad stuff that happens. So you have a trade-off there. So the essential idea behind our solution is use this erasure encoded data to send the original plus a little bit more. And then by doing that, you can overcome the network conditions at that time and reliably deliver the data in one shot. So you don't have this back and forth. Now, this is very simplistic. In the actual solution, it's a lot more interesting and complicated in that, in the sense that there's protocols between the sender and receiver where you're getting real-time feedback all the time from the receiver to the sender to tell it what the network conditions are, and the sender is dynamically adjusting how much of this encoded data to send at each point in time for each overall and for each block to make sure everything gets there reliably as quickly as possible. But underlying this, we're using the RaptorQ erasure code, which is standardized in the IETF. How many people know what the IETF is in this audience?
Internet engineering process.
Yeah, it's where all the technology on the internet is standardized, right? So this is this place where TCP and IP and UDP and everything else, that's where all the standards are, right? So this is in that, and there's a huge number of standards at this point, a lot of which are not even being used, but that's another story. But anyway, so RaptorQ is one of the standards in there, this RFC 6330. So here's conceptually kind of why it's important. So this labeling on the right here where it says unusable, impeded, frustrated good, we didn't make that up. It came from other people in the industry who looked at this and said, hey, this is what happens when people play games in terms of their experience. If the latency becomes, beyond 120 milliseconds or more, you just unplayable the game. And if it's actually not a great experience, even if it's like 110 milliseconds, and you're a little bit frustrated if it goes up to 50, and a good experience is 30, right? So that's what you'd like. You'd like to have this good experience all the time. And if you look at these retransmission-based solutions, this was actually based on sort of writing a little program to say, okay, under these loss conditions, what's the optimal you can do for retransmission? And so that's what this yellow line is here. Under certain loss conditions, you can't do better than this yellow line. Actual protocols are probably going to do worse than this. So you can see that it gets into some pretty frustrating kind of experiences for end users, whereas the BitRipple tunnel with the algorithms I'm going to describe in the next couple of slides a little more keeps it consistently in this good kind of regime here. So here's a little more detail on that. So here is what the network conditions were. It was kind of very good for a while, and then there was a spike, short spike for a fraction of a second, where the packet loss suddenly went up to 20%, and it spikes back down, and then it spiked up again at the end. The middle graph shows how much bandwidth the sender was sending across the network under these different conditions. And the orange shows what the optimal retransmission solution would do, and that gets the optimal amount of data across the data, which is the original size of data, compared to the BitRipple tunnel solution. And you can see that we use a little more because we do a little bit of proactive sending, but it's very banded and bound and not much more than the optimal. And you see it automatically adjusts. So this is the algorithms that I briefly described to you, automatically adjusting based on what the network conditions are, going up and down based on what's actually happening across the network. And this, again, this last one is what the result is. So this is what really people care about, is having this kind of consistently minimal latency for these interactive kind of applications. So this goes a little bit more into detail. This is kind of a typical streaming rate, for example, for GeForce Now game. Yes?
Some entry cost in terms of latency, just because you're using a FEC, right? The block. How much?
Yeah.
How much latency would be?
So it can be, that's one of the things that we really concentrate on, is to minimize that. And I'll explain a little bit more in a couple of slides about how we integrate this solution into actual deployments. And maybe that question is good there. But that's a great question. The processing that we do for the FEC is so tiny that it's insignificant. It's like a millisecond or two. It's almost zero, right? So that part doesn't matter. What does matter is, as you mentioned, is the block coming in. You have to cut the block, right? And so you have to make decisions on how to cut that block as it's coming in. One of the nice things we realized is that when they're doing these games and things like that, what they're doing is they're basically sending you a frame of video at a time. So you kind of get this burst of data coming at you, and you can encode that all together, right? So that actually doesn't cost you much time when you do it that way. Does that make sense? And on the receiving side, there you do have to gather and recover. But I'll give you some. I'll give you some idea of the numbers, and the numbers I'm going to show here have actually improved since I put this together.
Quick question.
Sure.
I guess I don't know how online gaming works well enough to know. Are they sending the whole picture, or are they just sending like the locations of the characters?
Oh no, they're doing. So I'll jump ahead.
Okay. No.
No, it's good to know, because when you look at the drills, it's good to understand how it works. So for example, GeForce Now or Xbox Cloud Gaming, both of these I'll show you some examples of later. Like for example, from Microsoft, they really have basically Xbox servers in the cloud.
They're just sending images.
You're sending everything from that. It's as if though, instead of having Xbox in your room that you're playing locally, you're playing with that thing in the cloud. Right? And so all the data, everything, when you do a reaction here, it has to go up to that server, do the reaction there, and come back to you. So that's really how it works for both of those, right? And actually, for pretty much all these cloud games.
It's a lot of data.
It's a lot of data. So just as an example, this is not unusual. This is kind of at the high end for Xbox, 10 megabits per second. It's kind of at the low end for GeForce Now, which is the NVIDIA gaming platform that's out there. So this is pretty typical on a mobile phone, for example, for GeForce Now, their rates can go much higher into the hundreds of megabits per second. And I'll show you an example. I don't have a video of that, but the next example of technical sort of covers that case. So here's an example. Again, this was not a real thing, but what we did is we're kind of in control of the network here. It's a 30 frames per second video, 40 kilobit frames. We injected these 3% spiky losses, so that's what this red line is here. This is mapped against the right axis. So you can see it's flat here. It jumps up to 3%, down, up, and so on. What the green is showing here is how much data is coming out of the sender side. And you can see, and one is kind of at, just sending the source data. So you can see it's kind of flatlined here. And then when it notices its packet loss, it ups a little bit. And then it comes down and up and down. So it's adjusting as the packet loss conditions change dynamically on a pretty fine time scale. And then this middle one is showing the reception side of that, right? So this is how much, this blue squiggly line is how many packets were received for each of the data blocks, again, scaled against 1. So you can see it's a flattened version of the green here because there's some packet loss, right? So this part, and it's noisy because of the packet loss, obviously. And then the top shows the end-to-end latency. So this is just the time to deliver from the sender to the receiver, do all the decoding, encoding, and everything else. And so the minimum possible here, in this example, it's a 40 millisecond round trip, so it's 20 milliseconds in one direction. So the minimum possible is 20, and it's just a little bit above that. Okay? Yes?
So are we talking about application level coding here, or is it at the lower level?
This is running in user space, so it really is at the application layer. So all our solutions really do, and there's nothing in the kernel or anything like that. It's really up at the application layer. This is a higher level one, so this is probably representative more of like a GeForce Now onto a full screen at high rate. So this 100 megabits per second, much bigger. And then the loss here was a stepped kind of loss. We started at 0 and stepped up to 3 to 6 to 11 and stepped back down. And you can see again how the bandwidth out of the sender adjusts as the loss varies. And you can also see that the blue is a flattened version of the green, right? So this is how much is received at the receiver. And you see there's a little more variability in the overall delivery time because these frames are bigger and so on. It takes a little more to get those packets across the network and process them and so on. But it's still pretty tight. Any questions about this? Because this is probably the last technical slide I have. All the rest is fun stuff.
Oh, well then can you distinguish between liquid data and data in other phases?
Oh yeah, okay. Liquid data just means it's encoded data. We just use that because there's this nice analogy of you kind of change a solid block of data into liquid form, in which case you don't really, like in a liquid, let's say you're thirsty, you're trying to fill your glass with a cup. This is an old digital.
Oh, it's liquid because it comes from the fountain.
Yeah, it comes from the fountain. Yeah, I'm sorry, I forgot we still had some of the liquid technology in here. But yeah, so it's easy to explain to customers and investors and people like that. They kind of really like that idea of the liquid concept because it speaks to them, right? Yes.
So what are the realistic packet loss rates? Here, are we talking about this over the internet or including the wireless hop?
So those vary. It just depends. So we're working with customers where it can be good a lot of times, but then it can be bad at other times, right? So it just kind of depends. And I'll show you some real world examples in a minute. Say a 10% is pretty bad. Yeah. 1% is not great.
1% is some kind of I think broadband or something survey that we did in terms of the packet loss rates.
Yeah.
I think around 1%. But you're right that maybe at worst it could be close to 10%.
Yeah, I mean, we've seen worse than that for sure. But actually, it's a good point. If you tried to play video, because video is so compressed, if you try to play it when it has 1% packet loss in it, it looks horrific. Especially the more it's compressed, the higher definition stuff, the more you try to play it with any kind of packet loss in it, it just becomes a mess. So it's really, it becomes even more important to kind of get it across reliably in those cases. So this is, okay, going a little bit into existing cloud services. So for example, I mentioned the Xbox Game Pass. That's the service from Microsoft, GeForce Now. Netflix has a new gaming service, which they announced in late last year. And I think it's actually out there at this point. Don't ask me why this is up there. I have no clue. That's just an anomaly. So one of the nice things about, and these are all kinds of different networks, so over Wi-Fi, over cellular networks, over satellite networks, and so on, in all kinds of different devices. So how does our solution integrate? So essentially, there's something we call the BitRipple Tunnel app that's installed on the end devices. And it really installs like a VPN tunnel. So I actually have it on this device here. And if I go under my VPN, it'll show me that I'm on the BitRipple tunnel. And then on the other end, for example, we have a server running up there, say on Azure or AWS or Google Cloud Platform. Right now, we have a bunch on Azure right now. And so what happens is so we can install this here and install this here, and then we don't have to change at all any of the applications, right? These guys, we don't interact at all with these guys or with any of the applications on the devices. It's just like a VPN, right? You turn it on, your data goes over it, and we accelerate the data between here and here, which is the part people care about, right? And from here on, it just goes natively to all these apps. So I can turn on the VPN on my phone, and you can turn it on in the sense that all your internet traffic goes over it, which means everything you send out goes between these devices and whatever that server is out there. Or you can selectively choose only these apps go over it, and everything else just goes normally. So this is what makes it. Got some of our customers really excited because they can see ways to deploy this where they don't have to go and talk to all these different companies to get it deployed out there. You can just do it independently of them. This is giving a little more detail in terms of how the setup actually works. So for example, the xCloud game services, for example, deployed in Azure East in Virginia. We don't touch that. We have an instance of an Azure server also deployed in East Virginia that's close to, but not in the same box here, right? So there's good connectivity between these guys. It's a clean, high bandwidth, no packet loss, wired network, no problems there. And so the connection is between this server and the end device, which is an Android device, for example, in Boston. And it's connecting over a Wi-Fi or a 5G or whatever kind of network. So this is going to show you an example. This was actually done by my son, who happens to be a student at Boston University over the Wi-Fi network there. And what we had him do is play xCloud gaming without the BitRipple tunnel, and then immediately after with the BitRipple tunnel, and see what the difference is. So that's what the top ones are, and I'll push this forward in a second. And then the bottom ones are, one of my colleagues has Starlink connection at his home. So he was playing the game over his Starlink connection, and the same thing. He tried it without and with, and you can see the difference. So let me play it forward. So which one would you rather play? All right, good. So that was xCloud. Here's another one. GeForce Now over that same Wi-Fi. Can you tell if it's with or without? So you can tell it's not great. So this is the map that tries to tell you what's going on around you. If you can look at that, you can kind of see that it's incredibly blurry. The whole thing is pixelated blurry. It's kind of a mess if you look at it. I actually did film a video of my son when he first played this. He first played it over the tunnel. He said, "Oh, it's not bad. It's working well." And then he turned it off, and he was just went, "Oh my God!" You know? So anyway, this is the version without, so we can compare what this one looks like in a second here with. So here's the one with. So hopefully you can see that there's a difference. Now what's really interesting about GeForce is they actually have more stats than xCloud does. So you can get this stats thing up here and you can see what rate the game is playing at, what rate it's streaming at. So this is what it's really sending. That's the rate of frames being sent to you over the network. This is they have a ping going all the time so they can tell what that latency is back and forth. It is higher here for the BitRipple solution than it is for the native one. This is an older version of the software at this point, so these numbers have definitely improved with our software at this point. But what's really interesting is this is clean, and the other one is really kind of a mess. So this one you actually can play the game, and the other one is very difficult.
So I have a question about compression. They're using some kind of video compression when they're transmitting, right?
Absolutely.
Independent of you.
Yeah.
When you see a frame, do you unpack it and do anything, or it's just the transmission's different? You don't do any different?
No, we don't do anything with the video itself. We're just, we're agnostic. In fact, you can send multiple applications. I mean, it's just like a VPN tunnel. You could send multiple streams over it all at the same time. It doesn't know, right? It just takes all the packets coming in, delivers all the packets to the other end, right? These guys, it's NVIDIA, right? So you can imagine that they have a bunch of GPUs up in the cloud that are doing all this generation of these streams in real time. That's why it works well with NVIDIA, right? They have massive horsepower behind this. So we have a lot of other deployment examples that I'm not going to go into any detail, but some of them we have customers who really are interested in delivering over, for example, Starlink networks, because those turn out to be pretty dirty, as you could see when you played the games over it. So when you actually send data over it, it actually shows the same characteristics. And when you use our tunnel over it, that makes it much cleaner. So for example, we have an aircraft manufacturer that wants to send real-time data over Starlink kind of networks. And that's something that's coming up. We have interest in AR, VR integrations, in drone integrations, and obviously in mobile devices, agriculture, telecommunication, robots, all kinds of other things. So that's kind of, I told you I'd be short, and I think I am. So that's pretty much it. Thank you.
Thank you for the great talk. Questions?
Thank you for the nice talk. So I've noticed that in the when you showed those 4 videos.
Yeah.
So somehow, even without the video on the top left seemed to struggle more than the one below. Was it because there was more variation in dynamics?
Yeah, exactly. That Wi-Fi connection sucks, to be honest. It's a Wi-Fi network at Boston University. That's not a very good one.
So somehow, like your solution is able to handle both like fast varying things and also like ones below, which was just somebody moving around, so maybe there's not as much action.
Yeah, so we don't really care what's going on. What we're trying to do is get that data from A to B as fast as possible within as few milliseconds as possible. And so whatever the app is on top of that, if they're slow-moving games, we don't really care. If it's fast-moving, it's more interesting, better in some sense. But a lot of the application, I mean, we do have some interesting things going on with some in the gaming industry, but also there's a lot of other use cases where you just need to get data from A to B really fast for any particular reason, right? Lots of different reasons. So that's what this solution is really designed for. So we're really, we're kind of agnostic to the applications that write on top of us, up to the point where if they don't really care about latency, why are they talking to us? Right.
Yeah. Do you have just a single route, or you have multiple routes?
So that's a great question. Our software does have the ability to do multiple paths, multiple routes. I didn't highlight that here, but we actually do have customers who are testing that out. There's one publicly, it's not really a customer, but we have a NSF grant up at Iowa State University, and they are trying it out for agricultural applications. When you have tractors, for example, deployed in the field and you have multiple networks, send the data over multiple paths and be getting some pretty good results there. It is much better that way.
To reduce the latency at the transmitter side, are you using systematic encoding or?
We are, but honestly, I'm not sure it matters that much. And the reason is because these blocks of data, these frames, in this particular application, in other applications, it does matter. So for example, if you have a steady stream of data coming into you, a packet stream, then, since they're spread out, you do care about how many packets are in that source block, because the more packets there are, the more time you have to wait, and there adds delay. And honestly, we will be able to, but we don't right now, be able to send that source immediately instead of having to wait for the whole thing to collect. For these gaming applications, it doesn't really matter that much, because what these guys tend to do is they burst a frame at you at a time. So it basically all arrives at the same time. So being able to send the first parts of that source out while you're collecting the rest doesn't really matter, because it all comes at you at once. That makes sense?
So in textbook function code, you have this 1-bit feedback. Do you also have it here, or you just do a batch? The 1-bit feedback is, I'm done.
Oh, no. So our feedback, it's lighter than, so for example, a TCP also has feedback, obviously, all the time. They're always sending feedback packets. We're sending less than that, but we're sending them continually, and it has other information in it, including, for example, how many packets has the receiver received? What's the largest sequence number it has received? And but from those two numbers, you can figure out packet loss, for example. Since you're updating that continually, you can figure out packet loss over small intervals of time and use that to adjust things. It's also sending back information about how many packets have we received from each block, how many more do we need, things like that, right? So it has a lot of other data, but it's all tiny, right? And the feedback packets are coming, every couple milliseconds or whatever, and they're small.
Is there any interaction with software-defined network where you can buy slices for large clients, or anything that is a market based on the quality you provide?
That's a great question. We haven't gotten that far yet. So we're kind of in the middle of this particular solution with the VIN kind of solution only came together in the last year or so. Before we had solutions which, for example, we had something deployed in a LEO satellite where they're actually running our software in a LEO satellite and beaming things down to Earth from there over a one-way channel. And it works really well, but it turned out not to be a very scalable market. So with this particular solution, it seems like there's a much bigger market opportunity, and we're exploring things along the lines that you're talking, but we're not there yet.
I have a question, which is, if I really want low delay, you have a knob, you can turn up more ECC, like you can get ahead of it and handle risk. Is there
Yes.
what's your trade-off? Like, why not send twice as much data and just really like, we never lose a packet?
Because bandwidth is supreme as well.
And my question is, do you pay? Is there a cost for that?
So
or is it just that you cause your own interference by
You
making?
cause your own interference. Yeah, you can cause your own interference. That's definitely for sure true. And also, there's just so much available bandwidth on some of these networks, right? So there's only so much room for overhead. Some customers don't really care. They're willing to, let it go.
Yeah.
Uses not twice as much, but a significant amount more. Actually, twice as much probably wouldn't help you that much. You probably do get in your own
There's
way.
an optimum there.
Yeah. So there's some point where just sending more really doesn't help. But there are knobs to turn, right? And that's also the other knob to turn is the length of that source block versus the overhead, right? Because if you make that source block longer in time and length, then the relative amount of protection you need to get it across the network reliably reduces relatively to the size, right? So the shorter the source block, the more kind of overhead there is in terms of how much you need to send to get it there reliably. So that's an obvious trade-off that we have the knobs to play with all those things, yeah.
So the source block contains many network packets?
Yeah.
And you can control that?
In fact,
Themselves are all variable length?
they can be whatever length they want to be, and we just take those, pack them, and redo them into our own packets.
And how big are they in the end?
So again, it depends on that trade-off we were just talking about. So for these gaming, actually for the tunnel in general, what we do is we have kind of a couple of timers there. One is to say we're only willing to wait this long after we receive our first packet of the new source block. We're only willing to wait this long before we cut it and send it, right? And typically it's like 5 milliseconds or something like this. And then we have another timer in there that says, okay, if we don't receive a packet for this amount of time, then cut the source block, right? And that's useful on the receiving side, on the client side, because the packet stream going back is pretty sparse, right? So you don't want to wait this extra 5 milliseconds. So you might set that to like 1 millisecond so that it goes immediately. And the bandwidth overhead is not that bad since it's such a low rate stream in the first place.
Great, well, thank you very much. All right. So